Hi, Mick McQuaid here. Welcome to week 2 of iste780, Data-Driven Knowledge Discovery. And this first day of week 2, day 5, we would like to go over a lot of material. In fact, in the next 2 days, we'll go over more material than we went over in the first week. So get ready for picking up the pace. Luckily, the topic is regression, which is probably familiar to many of you. But still, it's a lot of stuff. So let's get started. So in this video, I'd just like to talk about simple linear regression and the sort of subtopics of that: estimating coefficients, assessing the accuracy of the coefficients, and then assessing the accuracy of the model overall. So I'm going to just plow through the textbook and hit the highlights here. So the very beginning, I don't think you need any introduction to. I think the beginning is pretty easy, pretty self-explanatory. Let's move straight to the first picture here and remind ourselves of what linear regression is. So linear regression is finding the relationship between an input variable and an output variable. In this case, the input variable is television advertising. The output variable is sales. And we have training data, what we've observed. And what we would like to do is find a line. In the case of linear regression, what we would like to do is find a line that intercepts this cloud of points that relates this to this. And we want to find the line that is the best representation of the relationship of the input to the output. And so we need some kind of definition of what might constitute the best. And that definition is sort of revealed in this picture. So if we were to somehow find the line that minimized the size of all of these lines, these are all error lines, we've made a prediction here. And the error in the prediction is we erred this much in predicting this point. We erred this much in predicting this point. So if we could somehow minimize those errors, we would have the best line possible. And that's what linear regression is all about. And in fact, we don't even want to just minimize the errors, because if we were to just minimize the errors, what would be the problem? This line is a positive number. We take this to be a number added to the point where it intersects the line here. This is a negative number. We take this to be subtract from this number here. If we were to just simply add all these together, add all the positives up here and all the negatives up here, we would come out with 0 all the time, no matter how bad the line was. Imagine, for example, that we had a cloud of points that were exactly twice as far away from this line as these are. In other words, suppose that instead of being right here, this point is down here. Instead of being here, this point is up here. Imagine all of them are exactly twice as far away. Well, that line is strictly worse. Even though we have the same line, it's worse because there's more variability in the raw data. So we want to be able to represent that. So we want to get rid of these negative signs, and we can't simply blow away the negative signs. We have to do something that makes mathematical sense. So one thing we could do is take the absolute value. And we're not going to do that for reasons that I'm not going to explain. Basically, I'll explain the highlight of it, which is that the absolute value function is difficult to write proofs of. And if we were going to take a mathematical treatment of this course, we would have to prove every statement that we use. So we're using a bunch of tools. We're using a bunch of equations as tools, and we're not proving them. In order to prove them, we would need to be able to generate smooth curves, which we can generate by taking the squares of numbers and then taking the square roots of those squares. That gets rid of the negative sign, and the square and square root functions are smooth all throughout their range. Whereas the absolute value function is shaped like a V, so it's not smooth. It's got this kink in it. So we're going to take the squares of these and take that as a measure of how bad this line is, as how badly this line fits. And this textbook calls that the residual sum of squares, or RSS, and it's the sum of the square of each one of these. We take the square of this, we take the square of this, the square of this, and we add all of these together, and we get a number that we'll call the residual sum of squares. And so if these points were all twice as far away from this line as they are, that residual sum of squares would be much larger than it is. And here's the expression for the residual sum of squares. And so what we would wind up with when we minimize this, what we want to wind up with is a line. So what is the line? The line is the familiar equation y equals mx plus b, except that we will use slightly different terms than are used in geometry class. We're going to call this y equals beta naught plus beta 1 times x. And beta naught is this point right here, the y-intercept. And beta 1 is the slope of this line, the ratio of the line's rise over its run. And of course, x and y are simply the sample, the values that we have on at this point, at any point on the line. There's a corresponding y value and a corresponding x value. Okay, so that equation, and there are several versions of that equation here. Here's one for that example. Sales is beta naught, approximately beta naught plus beta 1 times television advertising. And the circumflexes, or carets, or hats that we put on here, which we pronounce hats, reflect that these are estimates based on the training data. Okay, now here are so if we were going to take a math approach, we could prove that these are the values of the coefficients that would minimize RSS. Okay, so this is the deviations of x from the mean of x, the deviations of y from the mean of y, and the deviations of x from the sample mean of x squared, the ratio of these things. So this is the ratio of the rise over the run of the points, which gives us the slope. And using the slope and the sample estimates, we can then get the y-intercept. And so now we have a complete description of the line. These two numbers together constitute a complete description of the line. What can we do with these? Oh, and here's the, I forgot about this. So this is what we would be minimizing if we were going to do the proofs. This is on the z-axis here is the RSS, the residual sum of squares function, and on the other two axes are beta naught and beta 1. And so we're at the bottom of this net, and this is a contour plot. You read this, that each point on this line has a height of 2.15. Each point on this line has a height of 2.5, and so on. So this is a contour plot done with numbers. We can also do contour plots with colors, which we'll learn later, instead of numbers. So this is the picture that we would be at least intuitively looking at if we were proving that these are the minimum points. Okay, so now there are a couple of things that we can do with these once we have them. Oh, and here's a picture of showing. So this is this black line here. Let me just zoom in on this. So this again is simulated data, so we know reality. Is it a black? No, it's a blue line. This blue line is our least squares line based on this sample. Because this stuff was simulated, we know the true line is this red line. And if we were to simulate with different samples, we would get a bunch of different lines, these light blue lines here, and they would all be kind of near the real line, but they wouldn't be exactly the real line. We would never know in practice, we would never know the real line. We would just know we were getting all these different similar lines. And this sort of suggests that if you have more samples, you might be able to get closer to the real line, because you can see that these all seem to converge on this real line. So that could be the intuition why a larger sample is a better reflection, or more samples are a better reflection of reality. Okay, so now what can we do with these? Oh, yet another thing I forgot to mention. So these are unbiased estimators. And what we mean by unbiased estimators is that they do not systematically over or underestimate the true parameter. And that's an important concept to know, that they are on average zero. On average, they converge to the true parameter. Okay, for the moment, I'm just going to skip these and go right to the confidence interval. So what can we do with these? We can establish a confidence. We can compute a confidence interval. Oh, maybe I can't skip these. I have to say what this. Okay, so each of these estimates has some variability, and this is a formula for that variability. So this is a formula for the variability of the intercept, and this is a formula for the variability of the slope. So each one of these has some variability. So we can say that we have 95% confidence that the true value of beta 1 is within 2 standard errors, that is, 2 of these, of the estimate that we have of beta 1. So, and this is in interval notation. So this represents 2 numbers. This expression right here represents 2 numbers, beta hat 1 plus 2.2 times SE, beta hat 1 minus 2 times the standard error. And this is confidence interval notation. This is typical interval notation, where square brackets mean that the interval can include the smallest number here and the largest number here. If we used, the typical notation would be if we used round parentheses, that we could get infinitely close to the edge, but this expression wouldn't quite reach the edge. But in any event, this is a 95. These are both notations for 95% confidence interval, and the same thing is true for the y-intercept. Okay, the other thing that we can do besides forming confidence intervals is make tests and form hypothesis tests. And the hypothesis tests always have this form, that there is, in simple linear regression, they always have this form. There is no relationship is the null hypothesis, and the alternative hypothesis, so this is H naught and HA. HA is that there is some relationship, and this corresponds to testing this versus this. I should point out that frequently we actually test that beta 1 is greater than 0 instead of equal to 0 versus not. We test that it's equal to 0 versus that it's greater than 0. Yeah, that's what I mean. So H naught is beta 1 equals 0. HA is frequently beta 1 is greater than 0, because it's often physically impossible for the slope to be negative. We know for sure, for example, if we add more advertising, unless the ads are really incredibly bad. Actually, even it's been shown that even if ads are incredibly bad, they increase sales. So we know that the slope, the relationship between advertising and sales is not going to be negative. We know here that what we're really testing is beta 1 is greater than 0. Okay, so how do we know which of these are true? We check the ratio between beta hat 1 and the standard error of beta hat 1. So this is the ratio of the estimator of the coefficient and the variability of the estimator of the coefficient. What is the ratio? So if the coefficient is big and the variability around it is small, then this number, the t statistic, will be quite large. If this number is very small and the variability around it is quite big, then this number will be quite small. So we would expect that this alternative hypothesis is true if this number is large. we would expect that this isn't 0 if this is large and this is small. Then the larger this is, the more certain we are, and the smaller this is, the more certain we are. So, but we take all of this as one number, one ratio, and I think we will see, here's a table of it. So if you were to do this on a calculator yourself, you would find that the ratio of this to this is this. So this, the coefficient divided by its standard error, gives you the t statistic. And the probability, this p-value thing here, is the probability of observing this t statistic or a larger t statistic if beta 1 is equal to 0. And this is very it's not easy to form an intuitive explanation of the p-value. And so this is one of the things that people get wrong the most in statistics. The p-value is a probability, and it's the probability of observing a value equal or greater than, equal to the absolute value of t or greater than the absolute value of t, assuming that beta 1 is equal to 0. The probability of observing this, in other words, if h naught is true. And if you try to rephrase this in different ways, my experience with students is usually when they try to rephrase the p-value to make it easier to express, they usually change the meaning of it. So try to understand it with the terminology here, difficult though that may be. Okay, now, how good is the model? So if we know that the model is predicting something, we know that the coefficients are good enough to predict something, we might want to go on to testing the entire model. And here is the statistic that we usually use to test the entire model. So there's an absolute value, the residual standard error, and then there's this kind of a rate. The r-squared value is a value that ranges between 0 and 1. So that's really an excellent measure. And the r-squared value is the total sum of squares minus the residual sum of squares divided by the total sum of squares. And that actually, believe it or not, will become fairly easy to remember. This is a pretty easy expression to remember. And this simply says that it's 1 minus the residual sum of squares divided by the total sum of squares. So let's think about what these concepts mean. There's the total sum of squares is all of the variance in the response of y. And this is all the variability irrespective of any regression that we do. And RSS is what's left over. So TSS minus RSS is the amount of variability that we've explained with our regression. And this textbook doesn't use any particular symbol for that. Other textbooks use a separate symbol. They have a symbol for all three of these things: the total variability, the variability that's unexplained, and the term that would be this, which would be the variability explained. But this textbook just uses that expression instead. Now, let's see, TSS minus RSS measures the amount of variability, and R squared is the proportion, the fraction ranging from 0 to 1 of variability that can be explained by this model. And so if R squared is close to 1, it means that this model has explained most of the variability in the data. If the R squared is near 0, it indicates that the regression did not explain very much of the variability. So in this example, where was the example we had here? 61%. In this example, it's explained more than half of the variability, but that's not a terrific amount. It depends on the context, though. It depends on how much of the variability you can expect to explain. There are some data sets that have a lot of noise. If the data sets have a lot of inherent noise, then it's not possible to explain much of it. And simple linear regression is, by virtue of its simplicity, easy to interpret. So we have to think about the fact that the 61% here might be very easy to explain, might be very easy to describe what we mean by that 61% of variability being explained by the model. Okay, and that's about it for this first part. Let's see. Oh, we have also the correlation coefficient. So this is the sample correlation coefficient, or Pearson's R. There should be like a little lowercase r here, I think. The correlation between x and y. And I should point out that this correlation, it says here quite correctly, is a measure of the linear relationship between x and y. So x and y could have a non-linear relationship. X and y could be very, very closely related without being correlated. So correlation just refers to linear relationship. We would need another measure to measure the association between x and y if that association is, for example, a hyperbola, or I mean a parabola. So if the relationship between x and y is curved, this is not a very good measure. Also, this is a measure between two variables. So simple linear regression is the case where p equals 1. So remember that n is the number of observations and p is the number of predictor variables. In the case of simple linear regression, we've restricted ourselves to p being 1. And so we can compute the correlation between x and y very easily using this formula. In multiple linear regression, the next topic that we're going to talk about, we cannot do that. In the next topic, we're going to have more than one x, so we can't compute this. So r squared, the r squared that we're talking about with the capital R, is the same thing as r squared with a little r in the case of simple linear regression. But unfortunately, this expression is no longer available to us. We have to actually calculate r squared for the capital R squared for multiple linear regression. So we need to know this formula. This is these pieces of information appear not only in the R output when we actually do, when we use R or any computer program to do linear regression. These pieces of information appear, and this piece of information appears, and you can see that you can get this piece of information from this piece of information. In fact, quite a lot of the output on typical statistics computer programs is somewhat redundant. It's just there for convenience. The same thing is true of the F statistic. We'll find, oops, where did the F statistic go? Somewhere, oh yeah, right here we see the F statistic. The F statistic is, we can glean from these pieces of information also. And we'll talk more about the F statistic later. The F statistic will become more relevant in multiple linear regression. So let's just summarize where we've gone, because you can see we're right up to multiple linear regression here. So let's just summarize where we've gone here with linear regression. So we've talked about the fact that we have this simple model, y equals beta naught plus beta 1 times x. And we've talked about the full description of this model being the coefficients beta naught and beta 1. We've talked about how we know that beta naught and beta 1 will minimize a quantity called RSS. And we talked about the fact that TSS minus RSS is the amount of variability explained. And and the fact that we can develop a 95% confidence interval around our estimates, that our estimates have variability called the standard error of the estimate. And we can develop confidence intervals around those estimates, and we can also perform a hypothesis test about those estimates. And if those estimates, and the way that we tell if the estimates are good is by a t-test, by computing a t-statistic, which is the ratio between our estimate of the coefficient and our and the variability of that estimate. And if that t-statistic is sufficiently large, that is to say, if the estimate is sufficiently large in comparison with its variability, then we believe in those estimates of the coefficients. Then we assess the accuracy of the total model by the extent to which it explains a fraction of the total variability. So we take the total variability and subtract from that the unexplained variability and divide that by the total variability, and we get a number which we call the R-squared statistic, which encapsulates the extent to which the model explains the fraction of variability explained by the model. So now, after all that, we're ready to move on to our next video, which will be about multiple linear regression. Thank you for your attention.